Welcome back, everyone. Now we have our second session. Welcome back, Gina ma'am.
Thank you, Namita. Let me share my screen. Hope my screen is visible.
Yeah, ma'am. Clear.
Okay, thank you. So welcome back everyone to the second session, Introduction to Deep Learning NLP. So this is not an introduction to the general deep learning. This is something specific to NLP. Some of the deep learning models that are popular in NLP will be discussing in this session. Okay. Again, we'll be discussing each of these models in much detail in the coming days. So the goal is to just give an overall introduction to various models and various applications of NLP, of deep learning in NLP, and how it is different from the traditional machine learning methods. So as I said, deep learning is a subset of algorithms in machine learning. So what is machine learning? We hear this term quite often these days, very often in these days. So what is machine learning? Or what set of algorithms do you call as machine learning algorithms? Machine learning algorithms refers to that set of algorithms where we do not explicitly code for the problem solving. Right? To solve a particular problem, we say that it is able to learn by itself. We are not explicitly telling the model or telling the algorithm how to solve the problem. So there is some sort of learning happening in that algorithm, and that's why we call it as machine learning algorithm. Or to be in very simple term, not a very formal definition. So talking about machine learning or deep learning in NLP, this diagram shows you the different. So in machine learning, when you're using machine learning for natural language processing, you input as a language text. So your first step is to do some pre-processing on it. Okay. So these are some of the pre-processing. Maybe very briefly, I will discuss what it is. In the afternoon session, I think we have a hands-on session on how to do the pre-processing or the text processing sessions, text processing in a NLP project. We'll be having a hands-on session by Dr. Manu Madhavan. So what's the first step? First step is to tokenize. We call it as tokenization. That is, given a text, you need to split it into different words. It may look very simple for us because all the languages that we know, or at least I know, English, Malayalam, Hindi, all these languages, the words are separated by spaces or punctuations. So very easily we can just cut the text into different tokens by searching for a white space or a token like full stop, comma or something. So tokenization is a process of splitting the text into different tokens, but in some languages like Chinese, this is not as simple as it seems because they don't use that space. Instead, they have different ways for tokenizing. That itself is a very researchable problem, tokenization. Then comes lemmatization and stemming, that is converting the words into its root form. For example, like words like steadying, playing, stay, steadied, steadies. So each of these words is a morphological variation of the root steady. So you might need to convert all these occurrences to its base. form. So studying, studied, everything has to be converted into its base form, and that is called as lemmatization. And whereas we have stemming, that is somewhat similar, but the difference is you just remove the morphological part and get the base. For example, studying, you again convert into study itself, but let us say all these are derived from the base word, let us say be. So all of this has to be converted into be. That is lemmatization, where stemming is just removing the morphological part and getting the root form. So there are different algorithms to do this. Then you may need to do POS tagging. So depends upon the problem. You may need all these steps or just some of these steps. POS tagging is part of this tag is nothing but the tags which you have learned in your higher school, like nouns, verbs, adverbs, adjectives. So given a text, identify what these tokens represent. Is this token a noun? Is this a verb? Is this an adjective? You give a tag to it. That is POS tagging. Next is named entity recognition. Named entity recognition we already discussed. For example, I'm giving a sentence. Capital of India is in Delhi or something like that. So India is a named entity, Delhi is a named entity. Or when they say COVID-19 shows symptoms like something. So COVID-19 is a name of an entity. So COVID-19 is a named entity. You identify what are the named entities. Next step is stop word removal. See, not all words in the text needs to, or not all words in text are important for the problem that you're solving. For example, words like is, was, the, most of the words are there just to be give grammatical structure to the sentence and does not contribute much to the actual meaning. So you may be able to remove this common words. That is stop word removal. That also depends on the problem. For some problem, these words are relevant, then you need to keep it. But for some problems, it may not be relevant. You can easily remove it. So these are stop word removals. These are some processing techniques you will apply on the text. Okay. Once these pre-processing techniques are complete, you can do the feature extraction. That is, how do you represent this text as a vector? We know all machine learning models need to represent its input in a processable format, that is in a vector format, as a list of numbers. Now how do we convert the text into this vector? This is where the feature extraction process comes in. There are different representation. One hot representation we will be seeing shortly in this presentation itself. Another representation is count vectors. For example, how many times a word occurs in a document? You want to represent a document. So you may say like sports occurs 10 times or medicine occurs this much number of times or something like that. You can have a vector where each dimension, like something like this, where each dimension represents a word. So when I say 5, it means that word occurred 5 times in the document. Maybe when I say 7, the second word occurred 7 times. So each dimension represents some word or maybe some context. And you can convert this text into a count vector. Then you may use another popular representation as TFID, term frequency, inverse document frequency. That is, instead of giving the actual count, you represented it as a ratio of frequency divided by how many documents this word occurs in. So just because by looking at the count alone, you may not get a clear idea of relevance of that word. So you may need to know whether that word is a rare word and how frequently it is occurring in other documents as well. This is another way of representing. Once you convert these vectors, this text into vectors, now you can give this as an input to a machine learning algorithm. Simple algorithms like naive-Bayes algorithm or SVM algorithm, simple logistic regression algorithms, and then it produces the results that you want. This diagram is for sentiment analysis. So the output is either a positive sentiment or a negative sentiment. So this is the basic pipeline of any machine learning algorithm. You have a text, you do a pre-processing, then you convert it into a vector by doing feature extraction. Feature extraction is the main highlight of this. Okay. So machine learning algorithm is, again, it's the same algorithm being applied to different problems. Your contribution as a researcher or as a developer who is developing this model, your main contribution comes in the feature extraction part. What are the features that is relevant to solve this problem? For example, you are doing sentiment analysis. So, as a domain expert, to identify which words. See, feature extraction. When I say it is a domain expert who is extracting the features, it doesn't mean that you have to hard code all the things manually. That you have to manually identify what are the positive sentiment words, what are the negative sentiment words. Need not be. Okay, you may automate this process, but the logic is written by you. So when I say, suppose we have a set of words that gives positive sentiment, set of words get the negative sentiment. For example, awesome, great, fantastic, superb. All these are positive words. Poor quality, weak. All these may be negative sentiments. All these words shows negative sentiments. So based on that, you can represent the text, or you can identify the text whether you can represent this as a in terms of these sentiments of the words. Okay. And then you may directly apply these modeling techniques on it. But if you are using naive-Bayes, all you have to do is you apply some techniques to find out. See, suppose you don't need a dictionary of words with all positive sentiments and negative sentiments. You can just use some supervised learning. So you have some text which is already labeled as positive. You have some text which is already labeled as negative. You may run an algorithm and to identify which all words has more probability of occurring in a positive document. Which are the words that have more probability of occurring in a negative document, and then correspondingly you may represent this as a feature. Okay. Basically, we need a domain expertise, or you may be applying in a healthcare. So you need a domain expertise who can tell you which features corresponds to which, so that you can model it accordingly. This is how a machine learning works. Traditional machine learning works. Then comes the deep machine learning part, where this feature extraction is replaced by dense neural networks, as you can see in the figure. Again, the pre-processing is much more optional in deep learning. In most cases, we tend to skip this part, but that also still depends. You can do it based on a problem. So first the text which is pre-processed, and then it is given, the raw text is given as input to the deep architecture. Here we don't need a domain expertise. Instead, this representation of text is automatically learned by the deep neural network, and directly the sentiment is predicted from this text. So this is how machine learning differs from a deep learning differs from the traditional machine learning things. It is in the representation learning part, or the feature extraction part. So why do we need deep learning in NLP? Like, see, why cannot we just do the feature extraction? Feature extraction has been working very well in many applications, specific applications. Feature extraction has been doing wonderful, but now why all this buzz around the term deep learning. Why do we want to switch to deep learning? Main reason is handcrafting features is often very time consuming and less generalizable. Okay. So when you come up with features, as I said, you need a domain expertise which doesn't come cheap, and then the time and effort that has to be put in. And if your features are not very good, then your output is going to be poor. Performance is going to be poor. For example, let us take a very general case. A typical classical example is identifying the fish from its length. Okay, so if length is not a differentiating feature and you decide to choose length as a feature for your representation, you may not be able to identify which fish is which from the feature, right? Or maybe when you talk about NLP, natural language processing, you come up with some features where it doesn't actually contribute to the problem at hand. So your model is only as good as the features that you identify. The second is DL can learn to recognize latent features from the data. So some of the features are not very obvious for the humans. There are some latent means hidden, some hidden features which we may not recognize, but the neural network is able to identify this latent features, some hidden features, some hidden patterns in the data, which the humans may not easily notice. This is one reason. Second reason is multiple level of representation that can be shared across tasks. Deep learning consists of different layers of neural network, and each neural network layer learns different level of abstraction. Okay. So this level of abstraction, it is much easier to speak in terms of image processing maybe. So in the basic level, the neural networks, the neurons are looking at each pixels. Then these pixels are combined to form lines or edges. Then the next layer, the edges are combined to form specific shapes at different level of. This is how an image is identified as a cat or dog. Similarly, in NLP, you can think of the lowest layer identifying words at that words, and the higher layer, maybe we are identifying some POS tags, or another layer we are identifying some grammatical structures in the language. So different levels of representation is possible in deep learning. The next advantage is in distributed representation or symbolic representation. So very classic example, let's say what is the meaning of life, or does anything like what's the meaning of dog or cat or anything I can ask. So all these are just some tokens in the dictionary which are symbols. Okay, now we may not be able to connect these symbols with each other. Initially they are discrete entities, a dog or a cat, maybe life, maybe trust, love. So these are just symbols that are represented by some vectors 0 0 0 0 1, which there is no way we can connect or find the relation between these symbolic representations. But whereas in deep learning, we use something called distributed representation, which can actually identify the connections between these representations. That is one reason why we use deep learning to learn representation instead of going for symbolic representation. So in earlier days, all the features or all the meanings were represented using symbols. But now these things have changed. Then maybe the last and the most obvious reason is it naturally handles the recursivity of language. Languages are naturally recursive, even though our vocabulary is very limited. Okay. When we have 30 million words, still our vocabulary is limited. Then the number of sentences we are able to generate from this is really huge. Maybe this is because of recursivity. We can recursively generate text from existing phrases. So languages combine to form phrases, and phrases combine to form sentences. Again, sentences combine to form documents. Different levels of recursivity is possible in language, and that is the concept defined behind deep learning also. So somehow those naturally they go hand in hand, natural language and deep learning. So to summarize this, deep learning is nothing but a subset of machine learning techniques. Machine learning techniques allows you to learn from data without being explicitly programmed, solve a problem without being explicitly programmed, whereas deep learning allows you to learn the representation also. That is where the difference comes in, the representation learning part or the feature extraction part, which is there in the machine learning, but is not necessary in deep learning. That is the main highlighted difference between a deep learning model and a machine learning model. So talking about NLP, so NLP, as I said, it's an age-old domain since 1950s or 40s. We were using rule-based NLP, where all the words were symbols. There were a set of rules which connected these symbols. So this, which was very well defined by some linguistics person. But just like in any other domain, writing language was expensive, need domain expert, was not very scalable. Then came the statistical NLP. Since 1990s, NLP has been using statistical methods. So here the rules need not be hard-coded. These models use statistics to learn rules, but still the features were handcrafted. Features were either handcrafted or they were explicitly coded to, models were explicitly coded to extract these features. For example, count the number of negative words. There's an algorithm which you can use to find a negative feature. Then still this needs a domain expertise. We need to know what are the positive words, or we need to know what are the common words in a spam. We need to know what are the common occurrence of words in a political article, if you want to categorize an article as political. So again, all this domain expertise were necessary. Since 2010, or let's say, with the coming of deep learning into NLP, it was around at this time, the first paper was published where this language model, deep learning model was applied to NLP. It was by Bengio in 2010, and came a new era of NLP called, which we now call as neural NLP. Deep learning NLP or neural NLP is also a term that is used in academia. So these models uses artificial neural networks. It can extract features from raw data, and it does not need any domain expertise. Okay. So simple example of rule-based model. Suppose you want to classify an email as spam or non-spam. So as a domain expertise, we may come up with some simple rules like spelling in a company name. Usually spams misspell the words in company names. So this could be one rule. How many misspellings are there? You can take it as a feature. 2, overuse of words like lottery, dollars. Yes, spams usually want you to click something. So they use many clickbait words. Maybe third rule is unnecessary urgency. So today itself, you have to do something, you have to send something or something like that. There is an urgency in the text. There may be use of inappropriate languages, again a clickbait. So these are some of the rules in rule-based system which can be used to identify an email as a spam or non-spam. But when you're coming to statistical NLP, we need not hardcode these rules. Instead, we may be using statistical models. Very simple example is a naive-Bayes classifier, which so you can run a simple algorithm to check the probability of an email being a spam and the probability of an email being genuine, and then compare its probability and identify whether that email is spam or not. So how do you compute this probability? You can apply a naive-Bayes theorem. You find out the frequency of each word in the document. You count the frequency of each word in the document. So probability is number of occurrence divided by total number of times the word occurs in spam or in. Okay, maybe I'm not going into that detail. So once you find the probability, you can just find which is more probable and identify whether the email is spam or not spam. Now, simple auto completion also using statistical NLP, that works perfectly fine. If you want to complete a sentence, I love chocolate, you want to predict the probability of the next word, all you have to do is, if you have a very large corpus, if you have a large enough corpus where you can find the probability of occurrence of the each word after chocolate. So you find the probability where cake, how many times cake occurs after the word chocolate. Count how many times chocolate cake happens divided by number of times chocolate occurs. Similarly, how many times chocolate drink happens divided by how many times. So just find the probability, and by comparing this probability, you can easily fill up this auto completion. So these are very simple models. In most of our actual real world problems, we still rely on statistical NLP. Even though this deep learning has become a very fancy word these days, most of the simple problems can be still solved using statistical NLP alone. Then comes the third phase, that's the neural NLP, which was inspired from human neurons or the artificial neural network. Here on the left, you can see a biological neuron. It consists of dendrites and synapses and the nuclei. So dendrites takes in input from various sense organs. It may be from sense organs or it may be from a previous neuron. And based on all the inputs, okay, some algorithm or some formula, it decides whether its synapses has to fire or not. So depending on the inputs as well as some known weights, we use the term weights. No, biologically, I don't know whether the biological people use the same term. Anyway, we mathematicians or the computer scientists use the word weights. So based on the inherent inbuilt weights and also based on the input that it gets from its different dendrites, the neuron decides whether it should fire or not. So this is the basic concept behind an artificial neurons also. Each artificial neuron has multiple inputs. It can take multiple inputs. So these will be some values. It could be some real values. I'm just using some values here. It could be some values. These values are multiplied by some weights. It is W0 into 1, W1 into 2, W2 into 0. And then these weights are summed up. And a nonlinear activation function is applied on this summation value. And depending upon this output, depending upon these values, the output is generated. Output, this is sigmoid neuron, so output would be between 0 and 1. This is the basic idea between an artificial neuron. Now, deep learning uses multiple layers of neurons, multiple layers of artificial. This is a single neuron, and just like biological neurons connect with each other, in a deep neural network, we have multiple layers. Input layer is a neuron which takes the input values, which is represented as a vector, and then there is a set of weights in each layer. So by applying this formula, at each layer, a hidden vector is generated, and this hidden vector becomes the input to the next layer. Output of each neuron forms a vector. So here you have some values. So here you have some values. Let us say, here you have some values. Let us say 1, 2, or 3, something, and then you apply this. You apply this formula at each neuron, and then you get some other values here, 0.7 or something, and then this vector becomes the input to the next layer. Again, this output of the second layer becomes input to the third layer. Similarly, there will be multiple layers, and at the final output layer, you have your desired output. Maybe this is sentimental classification. So first dimension is positive. So I'm getting 0.7 and 0.3. So since 0.7 is larger, we say this is positive sentiment. You are generating a probability vector for the output. So depending upon the problem, you may generate a probability vector or a regression value or something. This already I have explained. I hope this basic idea is clear. How neurons is applied at different layers to learn a hidden representation. So each of this hidden output of a hidden layer is a representation of your text. Each of this hidden layer output, or we call it as hidden vectors, output at each layer is a abstract representation of the input. I hope in the basics you might have already learned that how a back propagation is done. So once you get the output initially all the weights are randomly initialized. So you may have to train it in multiple epochs. After each training cycle, the values of these weights are adjusted. At some point, your model begins to make sense, and that is when you stop. This is a typical architecture of an elbow network. Just I put here just to show you how complicated the neural nets are. From a simple single neuron, how a deep neural network is developed, which contains thousands of layers and each layer having hundreds of neurons. Sorry, hundreds of layers, each layer having thousands of neurons. Coming to the text representation, how is text represented in a typical machine learning setup and a deep learning? I said the difference is mainly in the text representation. Traditionally, words were represented as one-hot vectors. As the name indicates, each word is represented by zeros and ones, and only one value, only a single value will be 1. All others will be 0. So this is dog. Suppose the index of dog is 10, then the 10th value will be 1. All others will be 0. Index of value cat is 3. So the third value will be 1 and all other values will be 0. This is a most simplest representation of a word, and size of the vector will be size of the vocabulary. So you have 1000 words in your vocabulary, you need a 1000 dimension vector. It's a sparse vector, and the main issue with such a representation is we cannot find any connection between these representations. For example, if you look at the distance between, how will you differentiate that dog and cat are similar while dog and table are not similar, right? We know dog and cat are similar. They have many common properties. They are living beings. They have 4 legs. They can sleep. They can jump. They both are mammals. There are a lot of similarities between dog and cat, whereas the similarity is not there in dog and table. But if you are using such a one-hot representation, the problem is these vectors doesn't have any connection. If you try to find a distance between dog and cat, you will find that it is same as the distance between dog and table. So this doesn't give any other information other than that they are separate vectors. Now, then came the distributional word representations. So to solve this issue, we came up with distributional word representation. It comes from a famous saying, you shall know a word by the company it keeps. Just like you say, you can know a person by the company it keeps. You can say a word can be known by the company it keeps. That is, words that occur in similar context have similar meaning. For example, look at this word. So this is taken from an NLP course. It is I have given the link here. It is a very basic course. So someone who is very new to NLP, it will be very simple and easy to understand this course. You can go through. So when you hear a new word which you don't know till now, how do you understand its meaning? We understand its meaning, we humans understand its meaning from its surrounding words or from its context. This is the idea behind distributional word representation. Can anyone make a guess what is the meaning of this word? Yes, you know? Can anyone make a guess what is the meaning of this word? Yes, you know? From the context in which it is used. It says a bottle of Testino is on the table. Everyone likes Testino. Testino makes you drunk. You take Testino. You make Testino out of corn. So from the context, you might be able to guess that this is some sort of alcoholic drink. Because we know words like wine may fit perfectly well in that context. You have a bottle of wine on a table. Everyone likes wine. Wine makes you drunk. You take wine. You make wine out of corn. I don't know whether we can make wine out of corn, but somehow this word wine seems to perfectly fit in this context. So since Testino and wine occurs in similar context, we identify that Testino should be something like a wine, which is a sort of alcoholic drink. So, and we use this information to learn a word representation. That is a basic idea. So we represent the word in terms of the context. So here, let each of the sentence be a context. The context need not always be a sentence. It can be a document, or it can be not instead of entire sentence. It could be just a window of words, maybe 3 words to the left and 3 words to the right, or something like that. You define the context, whatever is most visible for you. Okay. Now, let us see how we can represent other words also in the same context. So Testino, it occurs in all the 4 contexts. So it is a very simplified version. We are taking a vector of size 4. We have defined our context of just 4 contexts other. So Testino, 1, 1, 1, 1. 1 because Testino can occur in the first sentence. Testino can occur in the second sentence. Teschino in the third sentence as well as in the fourth. So it is all ones. What about the word loud? Loud cannot occur in any of these contexts. So we represent it as all zeros. Motor oil, it can occur in the first context. It cannot occur in the second context. It can not occur in the third context. It can occur in the fourth context. So we can represent it as 1, 0, 0, 0, 1, 0, 0, 1. Again, next word, tortillas, similar representation. Wine, again, similar representation. So wine can occur in the first 3 contexts, but not in the fourth context. So now we have 5 vectors represented in terms of its context. Is it better than the one-hot representation? It is not sparse. If you look closely, we'll see that words with similar meanings or words with similar rows have similar meaning. So Teschino matches the most with the word wine. If you look at vector difference, you find a vector difference between this, we will see that Teschino is closest to the word wine. So this way, distributional word representations is able to capture the context also in the representation. So again, this is also not a deep learning representation. This is mostly used in statistical NLP. Now, the third kind of representation, which is neural word embedding, is the representation that you use in deep learning models. So these representations are learned from the data without using any hard-coded. See, this representation we came up with, which was explicitly programmed. The frequency of each word was counted. Then we created a vector from this. But can we use deep neural network to automatically learn such a representation? Maybe not exactly this kind of representation, but some kind of distributional representation which will make sense, which vector space which makes sense. This is a neural word embedding. Here the goal is to learn an embedding weight matrix. An embedding weight matrix is just a collection of rows where each row represents a word. Suppose you have 1,000 words, that means you have a weight matrix with 1,000 rows, and each row represents a word. Maybe the first word is a cat, second is a dog, and third is a table. You can use a one-hot representation to just extract out this word embedding and then use it as a input to your model. So if you try to plot this neural networks, you will find that words with similar meanings or the words that occur in similar context will form clusters. So words like kitchen, vanity, sink, bathroom, bathtub, toilet, all these are forming a cluster. Maybe fan, light, LED bulb is forming another cluster. So words which occur in similar or which have some similarities, they are forming different clusters. Okay. So how do we learn this neural embedding? This is the topic for tomorrow's session. We'll be learning different text representation. How do you use neural networks to learn this? Neural word embedding has a very interesting property, very surprisingly interesting property. Suppose you take a vector of king, subtract it, vector of man from it, then add the vector of woman, you get a vector which is very close to queen. So king minus man plus woman is a queen. Uncle minus man plus woman is an ant, or maybe this sort of syntactic relationship can be found in this learned neural word embedding, and this is why we have become very popular. Now, script models we'll discuss in the next class. Next step is, so now we know how to represent words. There are different ways of representing words. Now, how we move on to the next step to represent larger text. Most of the times in the traditional NLP systems, we just combine these words using some simple techniques like addition, mostly addition. Actually, you find the vector for how plus vector of R plus vector of U will give you a vector for how are you. In case of one-hot encoding, in case of term frequency encoding, all those vectors, we could do simple addition like this. But this is not a very good representation. So these are some examples which highlight the challenges in this. For example, let us see, how are you? How old are you? What is your age? The first two sentences, they have a high word overlap. All the words are same. How are you are same. Only the word old is different. So probably if you are taking each vectors and adding it up, you will find that these two sentences will be closer to each other, whereas this third sentence, which doesn't have anything in common, will be very farther. But if you look at its semantics, the second and third sentence has to be more similar. So we cannot apply that same similarity technique here. We cannot identify similar phrases by using the vector distance. So people began to think of, like, can we come up with such a representation? Is it possible? Just like in the words, just like I can say dog and cat will be closer, or Testino and wine will be closer. Can I have a vector representation where how old are you and what is your age will be closer, whereas how are you will be further apart? This became possible due to this deep learning representations. Actually, we will see. Then second example is a case where a word has multiple meanings. So here the bank has multiple meanings, but how do we capture this meaning of bank in different contexts? So if you are going for a simple neural embedding, both the bank will have a same vector representation, and this difference may not be correctly captured. The third problem is paraphrase identification. So you have two paragraphs. You want to identify whether they are paraphrases. Paraphrases means same idea written in different words. So by just looking at the word vectors, by finding out how many words overlap or finding out how many words have similar meaning, can you identify the similarity between paragraphs? Is it possible? No, it's not possible. Actually, if you look at the word level, you will find that there is no much overlap between the words. So just by looking at the word overlap, or sometimes the opposite can also happen. Two phrases may have high overlap, but still they may have very different meaning. So just by looking at the occurrence of word, we cannot, or just by looking at some patterns, we may not be able to correctly identify paraphrases. So we need something more. We need a more concrete representation which can do this. And this is where all that automatic representation learning, deep learning and all came into play. So this is a typical deep learning NLP pipeline. So you have a text. The first phrase is pre-processing. As I said, it's optional because deep learning models are trained on very, very, very huge data. Okay, so when it becomes very huge data, studying and studies and everything comes quite a lot of time in the same context. So even if you learn different vectors for it, somehow it will all map into a very close space. So you don't have to worry about changing all the you don't have to worry about lemmatization. Definitely tokenization is required. You need to convert it in tokens, but lemmatization is not required, and stop words also doesn't create any problem. So it's also not mandatory. Next step is to learn a word embedding layer, that is to learn individual word vectors. So this in deep learning pipeline, we have a pre-trained set of vectors. So you have a dictionary. All these are dictionaries. When you say dictionary, we humans think in terms of word and its meaning. No, this is word and its vector. So you have a dictionary of vectors which you can directly download and use as weights in your embedding layer. These are popular word representations: word to vec, glow, fast text. All these are pre-trained vectors which you can download, but it's also possible to train your model to learn the word vectors of its own from the corpus. If suppose you don't want to use this, you can very well, if you have a sufficiently large corpus, you can learn the word vectors also. The first is tokenization, then you learn the word vectors. Now the word vectors is passed to the next layer where you learn the sentence vectors. So as I said, different layers of abstraction or different layers of representation learning. Learning word vectors, then learning sentence vectors, and finally the sentence vector passed to the output layer gives you the output probability. So with the coming of transformers, the sentence embedding learning also has become pre-trained. So that also will be topics for the coming days. Now, let me see the time. Maybe we'll stop in 10 minutes. We don't need a break now. Is it fine? I'll continue for 5 or 10 minutes and then we'll wind up. RNN and LSTM will be discussing in detail in the coming sessions. Encoder models, all this transformers also, I think it's already scheduled for Friday.
Ma'am, you can continue now.
Yes, I think I'll continue and we'll stop.
No, excuse me, you will be having a break, right? You need a short break, right?
No, I think we don't need a break now because we can just continue and in 10 minutes we can wind up the session. That would be fine, right?
One query is posted
In deep learning, how can we use it to identify the data leakage in business scenario, ma'am? Okay, sorry, sir. Like this, I'm not at all familiar with the deep learning used in business scenario, but definitely maybe I'll look it up and we shall discuss in the tomorrow's session. My area of research is in learning representation for phrases and sentences, and I'm working on problems in natural language understanding, like identifying, as I said, identifying similarity between sentences, identifying paraphrases. This is the main area of my research, that is learning sentence embedding and using it to identify similarity between text. But maybe I have some students who are working in hate speech detection and such areas, but business scenario is completely new to me. Maybe I'll look up it. So RNN, I think we will just leave this for tomorrow's session, RNN and LSTM, because both on Wednesday and Thursday, I think you have RNN session, and on Friday, I think there is a hands-on also coming up. So for time being, I'll skip through all this and directly go to some research directions in deep learning. These are some of the popular directions of research that is coming up in this. One is ethics in AI and NLP. You can see a lot of works coming up to identify bias in the model. Bias, when you say, see, you just maybe very simple autocomplete problem. Okay, so you are trying to complete a sentence. She is a dash, or she works as a dash, and he works as a dash. You will see that all the famous popular NLP models, some of the popular terms which you will hearing as GPT-3, or let alone, let us say the model used by Google or Facebook or whatever. See, all these have some inherent bias in them. So when you try to do an auto completion, to say she works as a nurse, whereas he works as a doctor. Or if you use a GPT-3, which is one of the most powerful language model available in the market. If you try to do an auto completion, all the 5 most probable words related to a female gender will be something like nurse, maid, housewife, teacher. So there is really a research paper on this. It's not something that I'm blabbing about. There is researchers going around identifying how much bias this model are. Whereas if you try to complete a sentence like he works as, it will be something like very prestigious jobs. Okay, so only there was a single job that came up in both that gender was waitress and waiter. Okay. But all other words had a very high bias in it. So how do you remove this bias from NLP? See, NLP, as I said, it is used in talent acquisition. So they found that the NLP models were rejecting applications based on their gender, where it was rejecting applications based on their geolocation. Even if the gender is not part of the resume, still deep learning models can identify the pattern. So there may be some hidden pattern in the resume which the humans may not notice. For example, a candidate coming from a all girls institution. Okay, so that is a clear hint that the person is female. Okay, or maybe the race, maybe blacks being left out from this recruitment. Okay, even if his ethnicity is not given correctly in the resume or is removed from the resume to avoid bias, still his geolocation may give a hint that he is of particular race. This was not explicitly programmed. We cannot blame the developer or whoever created the software. We cannot 100% blame them because they never explicitly coded all this in their NLP model. They didn't write the rules. They didn't do the feature engineering. But the deep learning models has picked up these hints from the text. And because the training data is already generated by biased human beings. So whatever bias that was in the humans is already there in the data, and whatever that is in the data, the NLP picks up. So this is ethics in NLP is a very hot topic at a very high level, like maybe Facebook, Google, or Amazon. At that level, ethics in NLP is being discussed in current days. And what about social responsibility that an NLP app should say? So recently, there was a news from Amazon Alexa. There's a news in the newspaper regarding Amazon Alexa, which told an 8-year girl to insert a coin between the plugs, okay, in the power socket. So why did Alexa say that? Actually, the girl was asking Alexa for some challenges. So it was initially giving some small challenges which the child could do. And when the child kept on asking for more difficult, tough challenges, Alexa came up with this answer that she could just insert a coin in the power socket. But thank God, the child was intelligent. The child did not try it out, but the mother immediately tweeted this, saying that okay, such an incident happened, and Amazon apologized, okay, publicly apologized and said that we have fixed the issue. But this is just one problem in a very large model. There may be many other dangerous things in NLP, which dangerous things is models may be picking up from the data. Alexa doesn't come up with its own ideas. It is just picking things from the internet and giving it to the user. So how do we make the AI responsible? How do we avoid such accidents? Is again a very interesting area of research. Then birdology, we didn't discuss birds, so leave it. Then how do we build models for raw resource language? So deep learning NLP requires high resources in terms of computation, in terms of training data. So how can we come up with low resource models? This is again an interesting area of research. And better training and test that the data sets are required. What about interpretability and explainability of deep learning models? So since we are not doing a feature engineering, the model is picking up the features. Will it be able to explain that this is the reason why the model has suggested so and so solution? For example, can the model say that it has classified the email as spam because of some of the pattern it has identified in the spam? Or maybe can the model say that it has predicted this disease in this patient because it has identified this particular pattern in the history? So will the models be able to do such level of explainability? Is again another interesting topic. So in image processing, we can see a lot of works going on in this area. In NLP, this is just coming up. It's very infant stage. In image processing, when suppose from a scan it identifies pneumonia, okay, it can correctly point out this is the area where it detected that, or it suggested that there might be a pneumonia. But such level of explainability, is it possible in a language model also? So another research area is, can we have deep learning models that are linguistically motivated? So most of the, see, once you convert the text into a vector, then everything is mathematics. So there is no much difference between the models that you apply in an image processing or a language processing or speech processing or whatever. Finally, all the models which will be learning, deep learning models will be learning, like CNN, RNN, LSTM, all these models, you can see that they are applied across many domains without any change. So what are those linguistic features which is going to make your model different? How you are going to improve it using the linguistic features? This is another area of study. And finally, there are many deep learning model architectures being proposed for different domain specific, for specific domains. This is another interesting path to take. So some domains we have already discussed in the morning sessions. So you can just take up an existing deep learning model and then apply it to your particular domain. You can think of modeling your domain specific problem in terms of these NLP task. What NLP task can you apply to domain specific model? I think that was a question also that came in the chat for a business scenario, how you can apply NLP. So that is it. Hugging Face and paper code. So those are again with deep learning models. Maybe we'll discuss it after tomorrow's discussion. I'll share some of these. I think we can wind up. Actually, I didn't discuss most of the deep learning models today because anyway, we'll be discussing it tomorrow. Why discuss it 2 times. So I hope you all got a very basic understanding of what is deep learning or why we use deep learning, and how it is used to represent language text. We will see very shortly in the tomorrow's session. That's all.
Okay, ma'am. If you have any doubt, you can ask.
Shivakumar sir, I don't know whether sir is student. Like anyway, can you just give a more? Can you briefly explain the question that you asked so that I can look up and get back to you?
Ma'am, good afternoon.
Good afternoon, sir.
Ma'am, how can we use it for detecting sensitive data leakage in business scenario, madam, using deep learning? Is it required to use the multiple combination of the technologies, or deep learning is enough?
Okay, sir. As I said, I will get back to this question in the next session, sir, definitely.
Sure, ma'am. Thank you.
Thank you, ma'am. It was
Thank you,
a
ma'am.
very interesting and effective section that we had now. And it was very useful for those who are interested in this area for work with. Thank you so much, ma'am.
Thank you.
Okay, our next session will start from 2 p.m. onwards, and the session is about basics of text processing, and will be handled by Dr. Manu Madhavan, sir. Now we can leave. Thank you, ma'am. Thank you, ma'am. We can see you next day.
Tomorrow.
Tomorrow.
Tomorrow we will discuss about one of the deep learning language model, that is LSTM, long short-term memory.
Okay, ma'am. Thank you. Thank you, everyone. You can leave now, and our third session will start from 2 p.m. onwards. And we have noticed some of you have attending this FDP sessions without registering. So if you possible, please contact me personally. I will put my contact number here in this chat box. Please contact me. I will help you to register once. Okay. I will put my contact number here. If anybody is here attending this session without registering, please contact me. I will help you to register. Thank you.